In section 4.5 we're going to be looking at kind of the last key to curve sketching, and that's looking at asymptotes. We have two types of asymptotes that we can look at in this particular section. There's other types of asymptotes as well, but we're going to be focusing on vertical asymptotes. And vertical asymptotes are always of the form x equal some value, because vertical asymptotes, as it would indicate, go straight up and down, and because they're vertical they always cross the x-axis. And we'll also be looking at horizontal asymptotes. We've talked about vertical asymptotes already. We haven't said too much about horizontal asymptotes. Now, horizontal asymptotes, because they run horizontal, are y equals some value line. So vertical asymptotes are x equals, horizontal asymptotes are y equal values. Now, vertical asymptote occurs where the function is undefined. An easy place to find where the function is undefined is to figure out what makes the denominator equal to 0. That's where we'll have a vertical asymptote. Now, the graph will never cross a vertical asymptote. And a lot of times we use VA to represent vertical asymptote. So again, a graph will never cross a vertical asymptote. Now the horizontal asymptote is a little bit different. First of all, a graph can cross a horizontal asymptote locally. And again, we're going to use HA here for horizontal asymptote, locally. But it won't cross it at extremes, meaning as we go out toward positive and negative infinity, it will not cross the graph, but it will approach a particular line at that point. Now, how do we find a horizontal asymptote? Well, to find a horizontal asymptote, we need to talk about limits at infinity. So the horizontal asymptote, and that again, that's HA. And again, a horizontal asymptote is some value, y equal line. And this line value, this L value, is equal to a constant. It cannot be equal to infinity, and it cannot be undefined. So this is equal to some value. So the horizontal asymptote exists if either one or both of the following limits exists. The first limit we'll look at is the limit as x approaches infinity of my function. So if I take the limit of my function as x approaches infinity and I get some constant, it can't be infinity, it can't be undefined, but if I get some constant, then I have a horizontal asymptote at whatever the constant is, y equal the constant. Also, I can take the limit as x approaches negative infinity of my function, and if I get some constant back, and it could be positive or negative constant, then I have a horizontal asymptote at that point. So this kind of takes the conversation into a little bit different direction, where we're talking about limits at infinity. We've worked with infinity and we've worked with limits, but we kind of have another set of rules here we need to look at for limits at infinity. There's three shortcut rules that will be really good to know for limits at infinity, and we're working with these right now in Calc 2, so you're going to need them later. First of all, let's look at a case where we're looking at the limit as x approaches infinity of something like 4x cubed minus 7x squared plus 1 all over 9x cubed minus 7. Well, if we, you can't plug infinity directly in, but if we approach infinity in the numerator, I get 4 times infinity cubed minus 7 times infinity to the 7th plus 1. We would get a negative infinity here. And the reason we get a negative infinity is this degree of infinity, x to the 7th, is negated by the 7, and this will be a higher degree of infinity than 4x cubed would be. And in my denominator, I'll get another degree of infinity. Well, infinity over infinity, or negative infinity over infinity, is an indeterminate form. So this kind of sounds familiar, indeterminate. And of course we know indeterminate means to do more work. Well, the more work that we could do is going to be a little bit different than what we used to be able to do. First of all, I don't see anything that we could factor or cancel, multiply by a conjugate. I don't see any of those techniques that we used to have. So we need a new strategy when we're working with limits at infinity. And the strategy for this particular case, and remember the strategy only applies when we have limits of infinity here, the strategy is to divide through by the highest power of the exponent in the denominator. So let's go ahead and look to see how that would work out. So we have the limit as x approaches infinity. Now the highest power of the exponent in the denominator is x cubed, so I'm going to go through and divide every single term through by x cubed. You can't just multiply the first terms or the denominator terms, sorry, that's x cubed. You have to multiply every single term through by 1 over x cubed or divide through by x cubed. Now the reason we are doing this, when we divide through by that highest power of the exponent in the denominator, they end up canceling here, and I should be able to get something where I do not have a 0 in my denominator or I don't have an infinity in my denominator. So that's kind of the strategy here. Now once I do this, I get all sorts of different things to start canceling and simplifying. First of all, my x cubes cancel totally. Next, it looks like we have negative 7x to the 7th over x cubed. That will leave me with an x to the 4th in the numerator. 1 over x cubed, can't do much with that, and negative 7 over x cubed, I can't do much there either. So rewriting this, I have the limit as x approaches infinity. See what's left. 4 minus 7x to the 4th plus 1 over x cubed all over 9 minus 7x cubed. Now let's go ahead and try and take that limit again. If I take my limit of 7 over x cubed, the 7 in the numerator is fixed. The denominator is increasing without bounds, so this piece goes to 0. 1 over x cubed will go to 0. And let's see what we're left with. The limit of a limit of a constant is a constant. Now, as x goes toward infinity, x to the 4th goes toward infinity, and I have over 9 here. So I have 4 minus infinity over 9, which is minus infinity. So the limit does not exist. But that also gives me some information here. Remember, in order to find a horizontal asymptote, I take the limit as x approaches infinity of the function. And what this is saying then is I have a horizontal asymptote at negative infinity, which means you don't have a horizontal asymptote at all, because I can't have a line at negative infinity because it's not a constant value. So what shortcut rule could we come up with here instead of doing all this work of dividing through by the highest power of the exponent in the denominator? Well, the key to the shortcut rules is to look at the highest power of the exponents in the denominator and the numerator. So here the highest power of the exponent in the numerator is 7. Here the highest power of the exponent is 3 in the denominator. So for this case, the degree in the numerator is greater than the degree in the denominator. So what that means is, as I take a limit towards infinity, the numerator is going toward infinity faster than the denominator. So for the overall fraction will go toward infinity. Now in this case, the degree in the numerator greater than the degree in the denominator implies that the limit as x approaches infinity of whatever function that is either equal to infinity or negative infinity, depending on the coefficient that we have here. So that's our shortcut rule. So if the degree in the numerator is greater than the degree in the denominator, the limit will either be positive or negative infinity depending on the coefficient. Now if you can learn these shortcut rules, you're really going to save yourself a lot of work. Let's go ahead and look at another example, and hopefully we'll be able to come up with another shortcut rule. Okay, so for our next one, let's go ahead and look at the limit as x approaches infinity of x squared plus 3x minus 1 all over x cubed plus 2. First thing we do is we actually just take the limit, and if we do that here, we get infinity over infinity. Infinity over infinity is an indeterminate form. Indeterminate form means to do more work. Well, the more work that we can do is to divide through by the highest power of the exponent in the denominator. So let's go ahead and divide through by that highest power and see how it affects our answer, and then see if we can come up with a shortcut rule. So I have the limit as x approaches infinity, and I'm going to go through and divide through by the highest power of the exponent in the denominator for every single term. Well, the highest power of the exponent in the denominator is x cubed, so let's go ahead and divide through by x cubed here. Every single term. Can't skip any of them. And then we start to simplify. Well, x cubes cancel here and leave me with a 1. Here I have x squared over x cubed, which leaves me with 1 over x. Here I'm left with 3 over x squared, and I can rewrite my limit. So I'm left with the limit as x approaches infinity of 1 over x plus 3 over x squared minus 1 over x cubed all over 1 plus 2 over x cubed. Now as we take the limit as x goes toward infinity, remember each of these numerators is fixed and the denominators are increasing without bound. So the overall fraction is going toward 0 for all of these. So I'm left with 0, but not 0 over 0. Remember I have a 1 here, so I get 0 over 1. So therefore this limit is equal to 1. Okay, well what shortcut rule could we come up with here? In this particular case, the degree in the numerator is a 2, the degree in the denominator is a 3. So the degree in the numerator is less than the degree in the denominator. This means that the limit as x approaches infinity of the function will always equal 0. Because the denominator is increasing faster than the numerator, the overall fraction goes towards 0. So here's another one that you'll want to remember. Let's go ahead and look at a third example, because if you think about it, we've looked at the degree in the numerator is greater, the degree in the numerator is less, and so the only case that we have left then is the degree in the numerator and the degree in the denominator are the same. So let's go ahead and look at an example where that's the case. Let's go ahead and look at the limit as x approaches infinity of 4x cubed plus 7x minus 12 over 2x cubed minus 1. If we take our limit, I get infinity over infinity, which is indeterminate. Indeterminate means 2. Do more work. Now the strategy that we're going to use is the same as before. We're going to divide through by the highest power of the exponent in the denominator. Now in this particular case, the highest power of the exponent in the denominator is a 3. So we're going to go through and divide everything through by x to the third. We can already see that a lot of these are going to go towards 0. So rewriting, we'll have the limit as x approaches infinity. Now 4x cubed over x cubed just goes to 4. 7x over x cubed goes to 7 over x squared. And minus 12 over x cubed, of course we can't simplify that. 2x cubed over x cubed is 2, and then here we're left with minus 1 over x cubed. Each of these terms where I have a numerator that's fixed and the denominators increasing without bound go towards 0. So I'm left with the limit as x approaches infinity of 4 over 2. And of course the limit of a constant is a constant, so I get 4 over 2 or 2. Well, is there a shortcut rule? Is there a faster way we could have worked this problem? Well, as it turns out there is. The shortcut rule here is if the degree in the numerator and the degree in the denominator are the same, if they're equal, the limit is the ratio of the leading coefficients. Now what we mean by leading coefficients is we mean the coefficient in front of the highest power. So it might not always be the first number listed, but it's the highest power. So in this case, my highest powers in the numerator and denominator were the same. I had a 3 in each. So the limit is the ratio of the coefficients in front of those highest powers. So 4 over 2, which in this case is 2. So those are the shortcut rules. And again, you'll save yourself a lot of time if you remember the shortcut rules. It's a lot easier than dividing through by the highest power of the exponent in the denominator. Now what we're going to do is to use these shortcut rules to learn about horizontal asymptotes. But before we work problems that actually have to do with finding those horizontal asymptotes, let's go ahead and summarize those rules that we've come up with so far. So first of all, if the degree in the numerator and the degree in the denominator are the same, the limit is the ratio of the leading coefficients. Now this is true whether we approach positive or negative infinity. Remember, all these rules only apply in this case where I have limits of x as they approach either positive or negative infinity. If I approach any other value like 2 or 6 or negative 12, these limit rules don't apply. If the degree in the numerator is less than the degree in the denominator, the limit is going to be 0, irregardless of whether I approach positive or negative infinity. If the degree in the numerator is greater than the degree in the denominator, and I'm approaching positive infinity, that tells me then that my overall limit is infinity. Now these rules down here, I don't really keep track of or memorize these. I kind of just remember these three right here. And then I remember that there's a special case here that this could be negative infinity if there's a negative coefficient. And so that's something that we should kind of keep track of a little bit. And we also have to keep track of whether your highest powers are even or odd. So these are all 5 of the rules. These 3 will get you where you need to go as long as you know how to do your algebra with the rest of them to figure out whether this should actually be a positive or negative infinity. And that will be based on whether I have positive or negative coefficients, even or odd powers, and whether I'm approaching positive or negative infinity. So definitely know these rules. Let's go ahead and look at some examples where we're finding these limits. For our first example, let's go ahead and take the limit as x approaches infinity of x cubed over x to the 5th minus 1 square rooted. So this is already a little bit different than we're used to looking at because I have a square root sign. Well, when we're looking at this, we really can't compare the powers in the numerator and the denominator directly. What I can do, however, is to go ahead and look at taking the limit. I get infinity over infinity. Infinity over infinity is indeterminate. Indeterminate means to do more work. Well, the more work we could try to do here is maybe rationalize the denominator, maybe something might factor, but really what we can do is apply those same 3 shortcut rules if we make one simple note. The square root of x to the 5th minus 1 is not equal to x to the 5 halves, but it behaves like x to the 5 halves. Now, where did x to the 5 halves come from? Well, remember, the square root means to the 1/2 power. Now we know, and I'm not even going to write this down, we cannot distribute this 1/2 to the x to the 5th or to the minus 1. So you cannot distribute an exponent across a sum or a difference. However, the behavior of these functions is going to be very similar. So at this point I can say, okay, 5 halves, that's the same as 2.5. So here the degree in the numerator is greater than how the denominator behaves as well, and so my overall limit would equal infinity. Now I have to support that. The degree in the numerator is greater than how the degree in the denominator behaves. Not what it's equal to, but how it behaves. So this is equal to infinity, and so this would, in terms of a horizontal asymptote, would mean I don't have a horizontal asymptote because I have a limit that doesn't exist. Let's go ahead and look at another example. In this example, let's take the limit as x approaches infinity of 3x to the 2/3 minus 5x plus 2 all over 2x plus 1. Well, right away you can plug in infinity or take your limit as x approaches infinity, and you get infinity over infinity, which is indeterminate, which means to do more work. Now when you look at this one, it's kind of a trick. Your eyes go to this first power, but that's not really where we want to look. We want to look at the highest power. Well, the highest power in the numerator is not 2/3, it's this implied 1 right here. Highest power in the denominator is this implied 1. So in this particular case, we have the degree in the numerator is the same as the degree in the denominator. Therefore, the limit is the ratio of the leading coefficients. The coefficient in front of the numerator is -5. The coefficient in front of the leading coefficient in the denominator is 2. So this limit is -5 halves. So don't be fooled. You know, it's not always the highest power that's going to be listed first. In this case, it's not. The highest power is listed later. So again, that's another spot that you can trip up on, so be careful of that one. In our next example, let's take the limit as x approaches not positive infinity, but negative infinity this time, of 7x squared minus 2x plus 1 all over x plus 1. Well, right away you take your limit as x approaches infinity, you will get positive infinity over negative infinity, which is indeterminate. Indeterminate means to do more work. Well, the more work that we can do is to divide through by the highest power of the exponent in the denominator if we want, or we can remember our shortcut rules. Well, if we look at this, as I approach negative infinity, negative infinity quantity squared will be a positive infinity. Let's look at the denominator. In the denominator, this will be approaching negative infinity. So if we look at the ratio of these, what's going to end up happening is I'm going to basically say the degree in the numerator is greater than the degree in the denominator. So that tells me right away that my answer is either going to be positive or negative infinity. And I'm going to look at this and say, okay, x squared divided by x is x. If I plug negative infinity in for x, I get negative infinity for my answer. So in terms of a horizontal asymptote, this would say I don't have a horizontal asymptote because my limit doesn't exist. My limit's at negative infinity. Now one thing that we forgot to comment on right here, this would say I have a horizontal asymptote of y equals negative 5/2 in the previous problem. Okay, let's go ahead and look at the same problem we just did, but let's change our limiting value. Let's take the limit as x approaches positive infinity of 7x squared minus 2x plus 1 all over x plus 1. And again, I get infinity over infinity on this one. The last one I had infinity over negative infinity. Both are indeterminate, which means to do more work. Now in this case, the degree in the numerator is greater than the degree in the denominator, so that tells me right away that my limit will be either equal to infinity or negative infinity. Well, if I analyze this, in my numerator, my highest powers are going to go toward infinity. In my denominator, it's going toward infinity as well. So I have a positive divided by a positive would be a positive infinity. Now, we're pretty good at finding horizontal asymptotes. Most of the ones that we've worked with so far, there is not a horizontal asymptote because my limit does not exist. But let's go ahead and find all the critical information, kind of go from first derivative all the way through second derivative and asymptotes of a function and graph it. So the function that we want to find all the critical graphing information will be the function 6x plus 7 over 3x minus 1. So critical graphing information, these would be things like the domain, the range, any x-intercepts, any y-intercepts, and some of these are going to be none, meaning I don't have a value. Vertical asymptotes, and remember vertical asymptotes are x-equal lines. Horizontal asymptotes, and remember horizontal asymptotes are y-equal lines. We're going to need the first derivative. We're going to need critical numbers, and from critical numbers I should be able to come up with intervals where I'm increasing and intervals where I'm decreasing if there are any. It's not guaranteed that there will be any. And I should be able to come up with relative extrema, so relative maxes and relative mins, again if I have any. And I should be able to look at the second derivative, and from the second derivative I should be able to come up with possible points of inflection. And remember, possible points of inflection might be actually possible lines of inflection, and then actually when I get done with those and check them in a concavity chart, I'll come up with points or lines of inflection if there are any. So let's go ahead and get started on our list here. The domain is pretty easy to look at. The domain basically can be any number except where the function is undefined. Well, we have a fraction here, and because we have a fraction I can look at the denominator. If I plug a 1/3 in here, I will get 0 in my denominator, so that tells me that my domain is saying that x cannot equal a positive 1/3. So this tells me right away I also have a vertical asymptote at positive 1/3. Now remember, with an asymptote I can't just put 1/3, I have to put x equal 1/3 because it's a vertical line. Now the range I'm going to leave out for right now because the range is a little bit difficult to come up with, and it's easier to look at your graph after the fact. X-intercepts, an x-intercept occurs when our y value is 0. So that basically means if I plug 0 into my original function, what do I get back out? Well, if I plug 0 into the numerator, I get a 7. If I plug 0 into the denominator, I get, let me see here, if I plug 0, okay, I was doing the y-intercept, sorry about that. If I take this function and set it equal to 0, I end up with 0 equals 6x plus 7 all over 3x minus 1. And then I multiply both sides through by 3x minus 1. And of course 0 times 3x minus 1 is 0, so I have 6x plus 7 equals 0, or x equal negative 7/6. That would be my x-intercept. Now for my y-intercept, I let x equal 0, and that's the one I started with here. If x is 0, I get 7 over negative 1, which is negative 7. So those are my intercepts. Those are where I'll cross the x and the y-axis, and they are ordered pairs. Now let's go ahead and look at our horizontal asymptote. For a horizontal asymptote, I take the limit as x approaches infinity of our function. and I get, in this particular case, the degree in the numerator and the degree in the denominator are the same, so the limit is the ratio of the leading coefficients, which is 6/3 or 2. And of course I need to say what my support is here, and that is the degree in the numerator and the degree in the denominator are the same. Now one other quick note for horizontal asymptote, you can't just put 3 or 2 or -5, you have to put y equal, and in this case we have 2 for a horizontal asymptote. Now a lot of this information we can get from the first derivative. So let's go ahead and look at taking the first derivative. Remember our original function was 6x plus 7 over 3x minus 1. So our first derivative, we can use the quotient rule, and we start with the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now that would be fine to leave this like this, except for a couple things. First of all, I have to set this equal to 0 and solve, which is not easy in its present form. And second of all, I have to take another derivative, and this is kind of a mess. It would be easier to work with this if I took a simplification of this and then another derivative. So in the numerator, I have 6 times 3x is 18x minus 6. 6x times 3 is 18, but I need to negate it, so I have a minus 18x minus 21. So when we simplify this, the 18x's cancel, and I'm left with negative 27 all over 3x minus 1 quantity squared. Well, critical numbers occur in two places. Critical numbers occur wherein f prime of x equals 0 and when f prime of x is undefined. Well, f prime of x will equal 0 when the numerator equals 0, and there's no way that negative 27 can equal 0, so there's no critical numbers for that particular reason. We do, however, have a critical number because this function is undefined at 1/3. So we have a critical number at x equal 1/3. But this is already a vertical asymptote, so we need to keep that in mind. So let's come up here and fill in a few more values. F prime of x was negative 27 over 3x minus 1 quantity squared. We had a critical number at 1/3, and now I can check the critical number in a slope chart to find out about intervals where I'm increasing and decreasing and any extrema. So let's go ahead and check this in a slope chart. So in the slope chart, it's just a number line. We put our critical number in and we put x equal, in this case, 1/3. And I'm going to be really picky about this, and you need to show all of your work for this. This is a number line. These are values of x down here. Now up here on the top, I'm seeing what's happening in these intervals from negative infinity to 1/3 and from 1/3 to infinity. So I'll plug in f prime at 1 and f prime at 0 as values that I choose. Now I chose these values because 1 is between 1/3 and positive infinity. I could choose any number between 1/3 and positive infinity, and I'm checking in my first derivative because I want to know what the slopes of the tangent lines are doing. I want to know if my graph is increasing or decreasing. Over here I have f prime at 0. I'm choosing 0 because I need a value between negative infinity and 1/3, and that's an easy value. I'm checking it in my first derivative because this will tell me what's going on with my slopes of my tangent lines. So if we look up here at my first derivative, I see something interesting right away. It does not matter what I plug in here. I can plug any number in here except 1/3, and I'm going to get a negative number back. Well, why is that? Well, the denominator is always going to be positive, because no matter what you have, a positive or negative value, when you square it, it turns out positive. And this numerator is always negative, so negative divided by positive is always a negative, and so that's where these values come in. I also should keep in mind that I have a vertical asymptote here, so this cannot be an extrema point. So there's the general shape of my graph so far. Now I don't have any concavity here. I have a negative sloping tangent line, and it can slope negative in two directions. One has positive concavity and one has negative concavity. And I'm not sure which one it is yet because I haven't tested this in a concavity chart, but I'm pretty sure it's going to be the one where we have negative concavity because of this asymptotic line. So intervals where I'm increasing, none. This function is continually decreasing because the first derivative is always negative. Intervals where I'm decreasing. Well, I'm decreasing from negative infinity to 1/3, and then I pick up again at 1/3 and go toward infinity. Now why can't you just say negative to positive infinity? Because at 1/3 this graph doesn't exist. This is a vertical asymptote here. So at 1/3 the graph is neither increasing nor decreasing, and the horizontal tangent line is not 0 either. It just simply does not exist here. Now because I do not have any changes in my slopes, I do not have a relative max or a relative min. So it looks like my next piece of information I can figure out is my second derivative, possible points of inflection, and a slope chart. Well, here's my first derivative, and so let's go ahead and use a rewrite of my first derivative in order to find my second derivative. I'm going to pop the denominator up top and give it a negative exponent so I can just use a chain rule. I don't have to use a quotient rule here because when I take the derivative of the numerator it will go to 0 anyway. So this is actually f prime of x. It's not f double prime yet. Now we have f double prime of x. I bring the negative 2 down, decrease the exponent by 1, and then multiply it by the derivative within. So it looks like in simplifying this, I end up with 162, so f double prime of x is equal to 162, and that's 27 times 2 is 54. 54 times 3 would be 50 plus 12, 150 plus 12 is 162. Negative times a negative is a positive, and here's my denominator. Okay, so there's my second derivative. Let's go ahead and plug that into my list of values here. Now I want to look to see where my possible points of inflection are. Well, possible points of inflection occur two places, where the second derivative equals 0 or when the second derivative is undefined. Well, there's no way that this can equal 0 because I just have 162 in my numerator, so I don't have any possible points of inflection because this cannot equal 0. This is undefined though at 1/3. That 1/3 keeps popping up in this one. So I have a possible point of inflection at 1/3. But we already know that that's a problem because 1/3 is a vertical asymptote. So if it does come out to be an inflection point, it's not going to be a point of inflection, it will be a line of inflection. But let's go ahead and check this in a concavity chart to see if I even need to be concerned about that. So in my concavity chart, again, this is a number line. I note my point of inflection, that's a possible point of inflection at this time. And then I check these values in my second derivative. So I could check something like 1 and 0. Well, the second derivative is not always going to be positive negative like the first derivative. If we look at this, the numerator is always positive, and the denominator, because it's cubed and not squared, could be positive or negative, so we need to check. If I plug a 1 in here, I get 3 times 1 is 3 minus 1 is 2 cubed is 8, and of course the numerator is already positive. If I plug a 0 in, I get 0 minus 1, which is negative 1. Negative 1 quantity cubed is a negative value. So for my concavity chart, I have a negative concavity and a positive concavity. And because we have a change in concavity here, you might say, oh, I have a point of inflection, but remember, we already know this to be a vertical asymptote. So it's not a point of inflection, it's a line of inflection. So we have a line of inflection at 1/3. So instead of an ordered pair here, we'll put x equal 1/3 as my point of inflection, or line of inflection is actually the case. So I'm going to take all this information and try and graph this. Now the only thing I haven't filled out is my range, and I'll do that at the very end. So my domain, vertical asymptote is at 1/3, horizontal asymptote is at 2. So let's go ahead and get started graphing this. First of all, because I have a vertical asymptote at 1/3, I have to make sure that I scale my graph correctly. So x equal 1/3 is an important point here. So x equal 1/3, I'm going to have a vertical asymptote. I also had a horizontal asymptote at y equal 2, so I'll call this point 2. And again, you have to scale these so we can see what's going on. Now remember, our concavity said to the right of 1/3, and that's right here. To the right of 1/3 I have positive concavity. To the left of 1/3 I have negative concavity. I have no extrema, and I also know that my graph, from my increasing and decreasing values in my slope chart, my slopes and my tangent line should always be negative. So I think this concavity is going to be something pretty important to keep a look at. So I need to fit negative concavity in here. Negative concavity does not fit here at all, no matter how I can try and plug it in, but it fits very nicely down here. As you can see, it's bounded by these asymptotic lines. Now over to the right, I need positive concavity. Positive concavity does not fit very well over here either. It kind of seems to fall away from these asymptotic lines or try and cross them, and that can't work. So that kind of gives me an idea that the graph occurs up here. Now, those are just kind of guesses. If I wanted to really know what was going on, I could plot some points. Now remember, my original function here was f of x equals 6x plus 7 over 3x minus 1. So let's say I'm not sure if I'm to the left of 1/3 whether I'm above or below this horizontal asymptote. So we just pick a point, and an obvious point to pick would be the one that we already looked at, and that's my y-intercept. So if we come up here and look, I had a y-intercept at 0, -7. So if I plot the point 0, -7, I'll say it's right there. That tells me I'm definitely below the x-axis. I have negative concavity and I have negative sloping tangent lines. Now my x-intercept was -760, so that's this point right here. So that's the point -760, and that makes sense. That seems to fall in line with that pretty well. Now, what hasn't helped me much is figuring out whether this is above the line y equal 2 or below the line y equal 2. Well, the easiest way to figure that out is to plot a point. So we could just choose some point over here to the right of 1/3, plug it into my original function, and see what we get. We'll see if we get a value more than 2 or less than 2. So we could plug in a value, let's say like 3, just to see what we get. So plugging in 3 up here, I get 18 plus 7, which is 25. Plugging in 3 into our denominator, I get 9 minus 1, which is 8. 25/8, that's 8 times 3 is 24 with a remainder of 1, so I get 3 1/8. So if I plug in a 3, I get out a 3 1/8, which has to be above. So that gives me the fact that I'm up here in this region. Now also I know that I have to have positive concavity over here because of my slope chart, and I need negative sloping tangent lines. So this particular graph has all the characteristics that we're looking for. The only thing I don't have here is my range. So in order to come up with the range, it looks like, and again, range are our y values. They go top to bottom or bottom to top. And it looks like my range are all possible values except y cannot be equal to 2 in this case. Now remember, horizontal asymptotes can cross locally but not at extremes, but this one didn't cross at all. So my range is all values except y cannot equal 2. So I have all my values there filled out, my derivatives, work shown, slope charts, concavity charts, and there's my graph. Let's go ahead and check this graph in Maple while we're here and see what we get. Okay, so Maple. Now remember, my original graph was 6x plus 7, 6 times x plus 7, divided through by 3 times x minus 1. So we'll check the graph first, or check the function first, and it's what we think. There's a lot of different ways to plot, but we'll right-click and plot, 2D plots. And not very useful. I can see something important is going on right here, but let's go ahead and change the scale. And it's usually the vertical scale that's throwing this off, so I'm just going to choose -25 to +25, and you could choose other values as well, but I think that this will just show what's going on here. So for this particular graph, it looks like it matches kind of with what I have, except this vertical line right here. And what Maple is doing is it's trying to connect positive infinity to negative infinity. So if we want to get rid of this line, I can use a different plot command. So I can use plot, put in my function, and then after my function I put a comma, and then I go discont for discontinuity equals true. Semicolon. Let's see what the plot looks like now. Still not good because of the scale, so let's go ahead and change the vertical scale. So I'll go -25 to +25. Looks better. So I've gotten rid of that vertical line. It still doesn't put in an asymptotic line for me, but it did get rid of the vertical line, which I knew wasn't correct. I'm going to go ahead and paste this into our journal doc and kind of compare it to the function that we have, or the graph of the function that we have, and see how it looks. One thing that this nice graph shows us up here is that we do have this horizontal asymptote at 2. This kind of shows that there could be a horizontal asymptote here, but it doesn't really readily identify it. It shows my graph is concavity-wise, negative concavity, positive concavity, and we can see that it does cross the y-axis here. And so our graphs match up really nicely. Now Maple does not show your vertical or horizontal asymptotes. Sometimes it will put in solid lines for them, but showing these asymptotes is really kind of important. It kind of brings the graph together. So again, while you're working these types of problems, please make sure you're using Maple, and using that discount equals true is kind of nice because it takes away those vertical lines that Maple puts in instead of asymptotic lines. Thank you.